is about intravascular pressure sensor. This is the first page for intravascular pressure sensor. Using an intravascular system eliminates the entire plumbing system by making the measurement at the site, as we mentioned before. Eliminate the time delay introduced by the tubing system, and also allows high fidelity measurement of high frequency components of the blood pressure signal. And for intravascular pressure sensors, we have two types of sensors. We can use various types of strain gauge bounded onto a flexible diaphragm at the catheter tip, and also we can use fiber optic systems where the displacement measurement of the diaphragm is made optically. In this slide, some applications of strain gauges have been shown. As you can see, some strain gauges like a metal foil strain gauge, some metal foil on a backing. Also some temperature compensated strain gauge. As you can see here, we have a strain gauge sensor with two elements. The first one is the main sensor. As you can see, we have a edge here connected to the diaphragm. We have a diaphragm here, as you can see. And the second element is also a strain gauge, but this element is not connected to the diaphragm. The pressure will be measured by this one, and this second strain gauge is only for temperature compensation. The first one is for measuring the pressure, and the second one is only to temperature compensation. It's for temperature compensation. And this is another view of the temperature compensated strain gauge under a microscope, and also other types of the strain gauge. As you can see here, these are some strain gauge, real strain gauge used to measure pressure. Gauges of this type are available in the F5 catheter. It means 1.67 millimeters in outer diameter. In the French scale used to denote diameter of the catheters, each unit is approximately equal to 0.33 millimeters or 1/3 millimeters, or 1 millimeters equals 3 French. And these types of intravascular strain gauge pressure sensors have some advantage and disadvantages. The main advantage of these sensors are their sizes. We can fabricate these types of strain gauges in small size, but we have some problems of temperature and we need to compensate the environment temperature to have correct measuring of pressure. Also, electric drift is another problem. Fragility, non-destructive sterilization, the price of these type of the sensors break after some use and also high cost per use are the main disadvantage of these types of the sensors. But nowadays, researchers, also the designers have solved these problems. Nowadays we have good strain gauge based sensors, intravascular sensors, without these disadvantages, because the advances, the improvement of the technologies in the fabrication of these types of sensors. As I told you before, the fiber optic intravascular pressure sensor can be the other types of intravascular pressure sensors, and these sensors can be made in small sizes comparable to those described in strain gauge, but at a lower cost. As you can see, the schematic diagram of intravascular fiber optic pressure sensor, we have two ways for traveling the light. The first one is from LED source to transfer the light to the main part of the sensor, and the second one is to collect the reflected lights to photo detector. As you can see, we have a chamber, we have a coating, and also we have a thin metal membrane at this end, distal end of the sensor, where the pressure will be applied to this metal membrane. Pressure, as I showed here, causes deflection in a thin metal membrane that modulates the coupling between the sensor and detector fibers. A light will be received here and will be reflected by this thin metal membrane. If this metal membrane is flattened, the reflection will be the highest. But if we have some deflection like this or like this, because some various pressure, the received light will be scattered or converged and cannot be collected by the um, collective fibers, by the detector fibers. Therefore, we will send a light with a specific intensity, and we will receive a light at the photodetector location, photodetector site. If there is no deflection, we have a good value compared to LED source at the photodetector. But if we have some deflection like these, we have a decreased value of intensity at the detection site. And for these explanation, we can plot the characteristic curve for the fiber optic pressure sensor. And as you can see, we have an increasing and decreasing part for various displacement. If the displacement is low, we have a high descent here, and also, as you can see, this part is linear. This part is linear, and the second part has a lower descent and also a non-linear. Lower descent and non-linear. Because the slope of the first region, first part, is high and the behavior is linear, we will choose the first one to use in our sensors. And also, we should emphasize that the ratio between the displacement and output signal is positive. But at the second part here, we have a negative ratio between the variation of signal and related displacement. Consequently, we choose region 1 in our pressure sensors, fiber optic pressure sensors. Let me review. We have a steepest descent, a steepest slope in region 1. Also, the behavior between the output signal and the displacement variations is linear, and also the ratio between the output signal and in brief, the slope is positive here and the slope is negative here. We will use the region 1 for our optical pressure, fiber optic pressure sensors. In this slide, some types of these pressure sensors, and as you can see, the real size of these types of pressure sensors, and also the sensor under microscope, you can see the microscopic image of the tip of these types of sensors in this figure. Some other types of the measuring also can be used. For example, the phase shifting can be used as the main index to detect the deflection at the diaphragm. If we send some light with a specific phase, the deflection can be changed, the received light at the detector side. Therefore, the phase shifting between these two lights can be measured for detecting, for calculating the pressure, and we can calibrate the deflection, the phase, the deflection, and the applied pressure. In this slide, we will talk about intracranial fiber optic pressure sensors. Measuring and monitoring the pressure of the dura in infants is important. Therefore, we should measure this pressure, this critical pressure after born, and to measure this pressure, we will measure the curvature of the skin surface of the membrane of the sensor, also the membrane of the newborn anterior fontanelle membrane. As you can see in this picture, in this figure, we have a sensor tip inserted into the brain and placed on the dura. We have a membrane here. This membrane, if is flattened, we have a reflector here, a mirror here, will reflect the transmitted light to the second fiber optic fibers to the detector. But if this reflector is not located at the optimum location, the reflected light will be decreased. Therefore, we will be able to find this situation. Okay, we should find the flattened situation of the membrane. We can't find it, but we should measure that pressure. Let me explain an important concept. If we have a layer, a border between two space with pressure P1 and P2, if P1 and P2 equals, this layer will be flattened. But if P1 is larger than P2, this border will be deflected. And if the P2 is larger than P1, we have something like this. Let me show here. P2 is larger than P1. We talk about the flatten of this membrane. If we have a flattened situation, it means that the pressure inside equals pressure outside. The pressure outside is the pressure inside our brain, the brain inside the brain of the infant, and the pressure inside is the pressure of something inside our sensor. Let me repeat it. P out is the pressure inside the brain from the perspective of the sensor. We are talking from the perspective of the sensor. The P out is the pressure. We should measure it. We want to measure pressure inside our brain, and P out is that. And pressure I is the pressure inside the sensor. If we make a situation with flattened membrane, it means that Pi equals P out. The flattened situation can be found by the reflected light, by comparing the reflected and the incident light. Okay, we found this situation. We found we have a flattened layer and we found that the Pi and P out is equal, is as the same. Now we should measure Pi. Measure the pressure inside sensor should measure. Therefore, we need another pressure sensor to measure Pi. Therefore, we need an ideal pressure sensor inside our measuring to measure Pi. Let me repeat it. To measuring the pressure inside the brain, we should find the flattened situation for the membrane. The flattened situation can be found by the monitoring the reflected and incident intensity of the light. After finding that situation, we know the pressure inside the sensor and the pressure outside the sensor is as the same. Therefore, at the next step, we should measure the pressure inside the sensor. Therefore, we need a pressure sensor. Therefore, this types of systems needs a second ideal pressure sensor inside their systems. You can read the text inside this slide by yourself. Fiber optic pressure sensors have some advantages. These devices are inherently safer electrically. We don't use any electric connection to the sensing side, to the detector side. The frequency response is not limited by the hydraulic properties of the system. And also there is no time delay because we don't have any hydraulic system. The fiber optic intravascular pressure sensor can be made in sizes comparable to catheter tip sensors, but a lower cost because all materials consist of some plastic or glass, and the price of these materials are low. But we have an important disadvantage. As I mentioned before, unfortunately, they lack a convenient way to measure relative pressure without an additional lumen either connected to a second pressure sensor or vented to the atmosphere. Therefore, we need a second pressure sensor, and also we need to have a system servo motor to control the pressure inside the sensor. We have a complex system at the outside, at the main part of the sensing device. Disposable pressure sensors, as you can see in these figures, decrease the risk of patient cross-contamination and reduce the amount of handling by hospital personnel. Reusable pressure sensors are subject to the abuse of reprocessing and repeated user handling. They tend to be less reliable than disposable sensors. These sensors should be cheaper, and also now we have cheaper and more reliable than reusable pressure sensors, as you can see. We usually fabricate these sensors based on MEMS technology. MEMS technology or micromachining silicon is the main approach to have some disposable pressure sensors. A pressure diaphragm is etched and photoresistors are diffused into the diaphragm for measuring its displacement. This process results in a small, integrated, sensitive, and relatively inexpensive pressure sensor incorporated into a disposable pressure monitoring tubing system. Contains a thick film resistor network that is laser trimmed to remove offset voltage and set the same sensitivity for similar disposable sensors. Thick film thermistor network is usually incorporated for temperature compensation, and also for the application of this disposable pressure sensor. Pressure sensors can monitor blood pressure in post-surgical patients as a part of a closed-loop feedback system. Such a system injects controlled amounts of the drug nitroperoxide to stabilize the blood pressure.